Electron affinity is the amount of energy that's associated with adding a single electron to an isolated gaseous atom. And just like with the ionization energy, even though we don't work with isolated gaseous atoms all that often, the trends still generally hold even under regular conditions. And most atoms are actually going to release energy when electrons are added to them. And using standard kind of thermodynamic conventions, that means electron affinities are usually negative. And the reason it's so easy to add electrons to atoms, so easy in fact that it causes energy to be released, is because most atoms actually have empty or partially empty orbitals that are available for the electrons to move into. And the trends for electron affinity are not as consistent as the other trends that you've learned about, things like size or ionization energy. They're generally a little bit less consistent. So the general trend is that electron affinities get more negative from left to right. So a more negative value means that it's easier to add an electron. And this should intuitively make sense. Because we know that metals tend to make cations, so they tend to lose electrons, and nonmetals tend to make anions, so they tend to gain electrons. So this trend should fit into your intuitive understanding of how atoms behave. So look at the second row elements, from lithium to fluorine. And you can see that although there are definitely exceptions, the trend is largely that the right-hand side is more negative, and the left-hand side is closer to being positive. If you look specifically at the p block elements in the second row, you can see a pretty obvious exception to the trend. So nitrogen is a positive value when you would expect it to be somewhere in between minus 122 kilojoules per mole and minus 141 kilojoules per mole. And the reason for this has to do with the electron configurations. So consider the electron configuration for nitrogen. If you write that p subshell as a box diagram, you'll see that all three p orbitals have a single electron inside of them. So to add an electron to one of those p orbitals involves adding an electron to an orbital that already contains an electron. So you'll have to place an electron into a fairly small volume in space, and you'll see a relatively large increase in the energy associated with the electron-electron repulsions. The other thing you might notice is that all of the electron affinities for the noble gases are positive. And this is because each of the noble gases has a filled p subshell, and adding an extra electron to a noble gas involves adding that electron to an orbital that's much higher in energy, the next higher n-value shell. The very general top to bottom trend in electron affinities is that electron affinities tend to get more positive towards the bottom of the periodic table, but this is a very weak trend, even more so than the left to right trend.